All right, we are moving on to the chemical equilibrium. Okay, so let's get started right here. In the past, we treated chemical reaction as they go in just one direction, just go forward, right? Hydrochloric acid react with sodium hydroxide, make sodium chloride and water. Silver ion plus chloride ion precipitate to silver chloride, right? Just go forward like this. Well, I have a confession to you. So I've been lying to you all the time. So anyway, so actually, I have been lying to you. Strictly speaking, all chemical reactions are reversible, but at a different extent. I'll give you some example here. So nitrogen dioxide is a brown gas, okay, and dinitrogen tetroxide is a colorless gas, so no color. If we start with the nitrogen dioxide, pure nitrogen dioxide, so in the brown gas, as the reaction goes, so we should see a colorless gas at the end. So gas, just the brown color just disappear, and we say, oh, that's when the reaction stop. All NO2 converted to N2O4, so no NO2 left, right? But in reality, this is what happened. Start with the brown gas of nitrogen dioxide, and over time this happened. Look at the color. It never goes to colorless. The color never disappear, right? Not completion. Now, if we go backwards, so let's say if we can make synthesize N2O4, just pure N2O4, okay? And then let it go over time. Let's see what happened. Look at the color. Turning brown, more brown, more brown, more brown, but not totally brown, right? Not in completion. So we have more concentration of NO2, of course, but lower concentration of N2O4. Well, surprise! What's going here? In the real world, most reactions don't behave as one-way completion reaction, right? Turns out they exist in equilibrium. Okay? Now, what do we mean by equilibrium? Before I explain the concept to you, let me give you two terms. Okay? First one is the forward rate, which is the rate of dimerization of NO2 become N2O4, and the reverse rate or backward rate. So it's the rate of N2O4 break down into NO2. Okay. All right. So let's take a look right here. Initially, let's say we go from NO2 to N2O4. All right. Initially, the concentration of NO2 is high, so they react to form N2O4 rapidly. All right. So the forward rate really quick. Right, and as they react to form N2O4, the concentration of NO2 decreases over time, making them less likely to collide. So have lower concentration, the rate go more slowly. Okay, so the forward rate slow down, slower. All right. Now, at the same time, N2O4 is being produced rapidly at the beginning, so the concentration go up high real quick. All right. As the concentration of N2O4 is higher, more N2O4, so there are more of N2O4 now. So they start to break up and make NO2, so go backwards. So the rate of going backward is faster over time, resulting the reverse rate speed up, and we see the less change in concentration of N2O4. Okay. Eventually, the two processes reach a point that they happen at the same rate, and at this point, there's no discernible change in concentration of both the product and the reactant. You can see the change now, right? And we call this point equilibrium. Note that I never say that the reaction stops. They never stop. Like never ever get back together. No, they never stop, right? But we see no change in concentration because the forward rate is equal to the reverse rate, right? And we end up with a mixture of the reactant and the product. Does it make sense? So the rate on a forward and backward, they are equal. So it just go in cycle. Okay. Now, so here's the concept of equilibrium. But now let's focus on the result of equilibrium that give us a mixture. So the word mixture is kind of sad news for chemists who make their living from doing reaction to make products. So chemists, of course, they want to make the product, right? Because no matter how many reactions they do, they will end up with a mixture of the product and reactant. But don't worry, chemists are smart. They find a way to employ, stay employed in this world. So by doing the following, okay. All right, so since most reactions are in equilibrium, so we're giving the mixture of a reactant and a product. Well, the word mixture is kind of broad, is a broad term. Is it a mixture of 1% reactant and 99% product? That's good. That's a lot of product. That's what we want. That's cool. Equilibrium, who cares? We got a lot of product, right? Or 99% reactant. That's bad. Or 50-50, but that's not really good, right? So chemists are interested in the position of equilibrium. If the equilibrium lies to the product side, reactant side, or 50-50, somewhere in the middle. Okay, could be 48%, 52%. I mean, it's somewhere in between, right? So chemists express the position of equilibrium by Kc, okay, which is the equilibrium constant. C stands for constant. Hold on. Okay, C stands for concentration, right? And they call the value, and the Kc can be expressed as the concentration of the product over the concentration of the reactant, and both concentrations are raised by the power of the coefficient in the balance equation. So you have the balance equation all the time, right? So y and p. So we do concentration of p to the y and concentration of r to the x. Okay, so and chemists use this equilibrium constant to determine the position of equilibrium. Let's talk about Kc on the next video. Okay.